welcome. So, in the last lecture, we were discussing rather recalling the concept of Riemann integration, and let us have a quick review of what we did in the last lecture. Is that if f is a bounded function defined on a b to r, then we are first we are taking a partition of a b as a is equal to x 1 less than x 2, this is less than x n, which is equal to b, and then we define the Riemann sum f with a corresponding partition p is equal to summation over f of c I and delta of x I and I from 1 to n minus 1, and C I is nothing but this belongs to any point on x I or x I plus 1. And then we define the norm of P is the maximum of delta x I and 1 lesser equal to I lesser equal to n minus 1, and then we define the integral a to b if the limit exists. If this limit exists, then we say that f is Riemann integrable and the integration of f is this. Okay. So, now let us look at the very standard properties of Riemann integration, that we know that it is integral is linear. That means, if we take alpha f plus beta g and we integrate, then we can pull out alpha from the integral, and then it will be alpha times a to b f of x dx, beta times a to b g of x dx for all alpha beta in R. And now, if we have a to b and then c is a point there, then we can calculate the integral a to c f of x dx and c to b f of x dx. If we add them, then we are going to get the integral from a to b. So, that is also trivial because the partition of a to c union the partition of c to b, it is almost a disjoint partition. So, we can take their sum. Monotonicity, if f of x is lesser equal to g of x, then f x integral over f of x dx is lesser equal to g x dx, that is we know. Then this is important, is that one of the most important thing which the Riemann integration tells, that actually the integral what we have learned in high school, that it is antiderivative, it is the same as the way we are defining the Riemann integration. So, what does it say is that in high school, remember that we have defined the integration as an antiderivative, and exactly this is what it relates, that this prescription of Riemann, it is going to, if you do perform the integral, this is nothing but the antiderivative if you have a nice function. So, now if f is continuous and integral and capital of f of x is a to x f t dt, then f prime of x is equal to f of x. That is the antiderivative part, which is saying that this f prime derivative of the integral is nothing but the function itself. And then there is another part of fundamental theorem of calculus, that is the evaluation part, and that it says that suppose you are doing with the f prime is Riemann integrable, you are starting with f is a function which is differentiable, then f prime is Riemann integrable. It is not necessarily that if I take a function f which is a differentiable function, then the f prime is going to be differentiable or not is not known to me. At this stage, we need, which in fact will not be true, we need to impose the condition that f prime is Riemann integrable. Then a to b f prime of x dx equal to f b minus f a, that is the evaluation part. Okay, so this is the standard stuff of Riemann integration. So, one of the flaws in the Riemann theory of the Riemann integration that it is not very well behaved with respect to convergence of sequence of functions. One would like to ask, suppose we have sequence of Riemann integrable functions and f n x converges to f of x for each x. Will it be true that f n x integral a to b converges the integral a to b f of x dx? If f n converges to f, does it imply that integral of f n converges to integral of f? So, which may not be true. You take the function, for example, f n x is n 0 to n. So, now let us f 1 is this, f 2 is here is 1 by 2 and then this is 1, then f 2 is up to half, this is 2 and from half to 1 this is 0. Similarly, f 3 you can define if it is your 1 by 3, then here it is taking the value 3, then 0 here up to 1. So, now where does this function converge? Now, I take a x in 0 1. Now, wherever the x is, however does not matter however close it is to 0, I can always get a n such that 1 by n is less than x. Now, if I suppose this is my 1 by n sub naught. Now, any n bigger than n sub naught, 1 by n is going to be less than 1 by n sub naught. Therefore, all these 1 by n will like over here. Now, for this x, f n of x is equal to 0 for all n greater or equal to this n naught. Therefore, this function f n is now converging where? It is converging to the 0 function. Okay. Now, if I take the integral from 0 to 1 f n x, so this is going to be n into 0 to 1 by n dx, which is equal to n into 1 by n, which is equal to 1. And now, the integral of the 0 function, because f of x is 0 here, therefore, 0 to 1 0 dx, this is equal to 0 and this is 1, which does not converge. So, Riemann integration in principle does not really respect the pointwise convergence. However, if f n converges to f uniformly, then we have got the result that a to b f n x dx converges to integral a to b f of x dx. So, just the pointwise convergence does not give us the required result. Okay. So, now the series f n x converges uniformly to f of x, then f is Riemann integrable and a to b summation n from 1 to infinity f n x dx, we can interchange the limit and the sum. Because what is this? This summation of n equal to 1 to infinity f n of x, this is actually limit of n goes to infinity summation n from 1 to n f n of x. This you can call it as S n of x. So, now this is what we are interchanging, is that here the convergence is uniform, therefore, the limit can be interchanged with the integral. This essentially is saying what? Limit of n goes to infinity a to b f n x dx is equal to a to b limit n goes to infinity f n x dx. That is what the meaning of this statement is. So, we can interchange the limit and integral if we have uniform convergence with us. So, that is an easy consequence that the sum is nothing but the limit of some partial sum, then the by the linearity. So, here what you have got a to b, this is limit of S n, which is I know that this is uniformly convergent. So, I pull out the limit, I have a to b S n. Now, this S n is nothing but the finite sum. So, by linearity of the Riemann integral, now we can interchange this finite sum with the integral, then what we get is the appropriate result over here. Okay. So far so good. Now, what we have seen in the first lecture, that we asked ourselves the question, what Fourier claimed that given any 2 pi periodic function, we can have a representation of that function through cosine and sine, that is e to the power, it can be represented in form of the Fourier series. So, before addressing that problem, so let us make ourselves little familiar with the periodic function. So, now what is a L periodic function? I take a positive L. Now, we define a function f from R to R, and we say that f is L periodic if the function f of x plus L is equal to f of x for every x. That means, after the length L in, suppose if my L is 1. So, if I have a function like this from 1 to 2, then I will cut this and then I will paste it here. Every one interval, this is going to be repeated. You just cut the 0 1 and put it between 2 and 3. So, this is what is the periodic function, and if here my L, we are taking it to be L is equal to 1. So, that is what means the periodic function. So, for example, you can take f of x is equal to sine 2 pi x L. Now, then f of x plus L, this is equal to sine 2 pi x plus L divided by L, which is equal to sine 2 pi x by L plus 2 pi L by L, which is 2 pi. Now, we know that sine 2 pi plus theta is equal to sine theta. So, this is sine 2 pi x by L, which is nothing but f of x. Similarly, cos 2 pi x by L is L periodic function. Now, for a general thing, what we will see is that now you take, we are doing it f is a function from R to R. Now, I take a x in R. Now, our L is fixed. Now, we can find a n such that x is going to be in this interval n to n plus 1. So, there will be some n in which it is going to lie. So, I define f of x is equal to x minus of n L. That means, basically now I am defining for all practical purposes that f is from 0 to n l, 0 to L. So, now f of x plus L, this is going to be x plus L minus of n L, which is equal to x minus n minus of 1 L. Now, if x is lying between n L to n plus 1 L, then x plus L is going to lie n plus 1 L to n plus 2 L. Now, f of x plus L, this is equal to x plus L minus n plus 1 L, which is equal to x minus of n L. This is nothing but f of x. Therefore, this is a L periodic function. So, now given a function, how we are going to extend that to get the L periodic function. Now, suppose I have a function which is defined on 0 to L. So, like pictorially we are saying that how to get the L periodic function on the throughout which is defined throughout R, that whatever the picture of the G in 0 to L, we just got that picture and paste it at L to 2L, then 2L to 3L, minus L to 0, minus 2L to minus L, like this. What we are going to get is a L periodic function. So, we can that means we can extend G to a L periodic function as follows. We just define, now G is only defined here from 0 to L. Now, if our x is somewhere here, how we are going to extend this? Just like in the previous example what we have done, that if we have a x wherever it is, there will exist a n such that x is going to lie in this interval. So, now you define a new function f of x, which is equal to g of x minus of n l, if x is lying between here. Now, this f is now defined throughout R, and then if I take f of x plus L, then easily, like the last time what we compute, we are going to get that f of x plus L is equal to f of x. Okay. So, let us see some concrete example. So, now I take g of x is equal to 1 if x is between 0 to 1 half, and this is 1, and it is only defined on 0 to 1. Now, we want to extend this function g to whole of R such that the extended function is going to be 1 periodic, that is what is our goal. So, now what we do is that this is 1, this is half, then this is 3/2, this is 2, like this, this is 5/2, like this we extend. So, cut this, paste here, paste here, paste here. So, this extended function is going to be 1 periodic function and which is defined on whole of R. Similarly, suppose I have a function here and suppose this is minus 1 half, this is 1 half, this triangle function, then how does the extended function will look like? This is what it is going to look like. The copies of the triangles have been pasted. So, now let us be when we are extending the function from an interval, then interval plays a major role. Now, let us see, suppose I have a function which is defined from minus pi to pi, f of x is equal to x, and I want to compare with that the function which is f of x equal to x, but on 0 to 2 pi. You see, from here if I am shifting by 2 pi, I am not going to get 0 to 2 pi, because I will get pi to 3 pi. So, how does this function look like? Suppose if I am taking the first one f of x equal to x from minus pi to pi, then this is the graph of the function. So, now I will cut and paste it from pi to 3 pi, I will cut and paste it from minus 3 pi to minus pi. So, this is going to look like this periodic extension. On the other hand, if I look at this function, so from this is 0 to 2 pi, this is x. Now, I am cutting it from 0 to 2 pi and putting it from 2 pi to 4 pi. As you can see that this function and this function is different. So, it is very important to determine when we are talking about the extension of the function from an interval. So, this interval plays a major role. So, now this periodic function is what? I mean, intuitively you see that, I mean, it is defined on an interval. So, just think that we are kind of, if we bend the interval, then the two endpoint, if we join, if we merge the two endpoint, then what we are going to get is a circle. So, now it is natural that if I have a L periodic function, then I can think of that function as a function on the circle whose circumference is L. So, how do I write this? We will identify any L periodic function f on R with a corresponding function capital F defined on the circle T L. T L is nothing but where the circumference is L, and I am doing it the center at the origin, where f of x is equal to the cap some. Now, f is defined over here. So, this is L by 2 pi, and this is nothing but the 2 pi I x by L. This is the argument part and this is the radius. Okay. So, a function defined on 0 L is continuous. We will say a periodic function defined on 0 L is continuous if it is continuous at every point of 0 L. So, an L periodic function f is continuous on T L if it is continuous and f of 0 is equal to f of L, because we are identifying 0 and L point, therefore, f of 0 has to be equal to f of L, then we say that it is continuous on this entire circle. Okay. A function 0 L to C is said to be piecewise continuous that if it has finitely many discontinuities. So, this is a picture of the piecewise continuous function. You can see that this at this point it has a discontinuity, this point it has a discontinuity, at this point it has a discontinuity, and then if I take the, suppose this is my L, then you cut and paste like this. So, now it has finitely many discontinuity. So, now we can talk about the integration of the L periodic function. It essentially what I need to do is that I need to integrate from 0 to L f of x dx. Now, suppose I have a periodic function, intuitively let us try to see 0 to L. So, now I have this function. So, now periodic is going to be a copy of this is 2 L like this. So, natural thing is that the integration is nothing but the area under the curve. So, intuitively as you can see that, suppose I start at this and I take a length of L, then whatever I am missing out from this is been incorporated here in this interval. So, in every interval of length L, then what we are kind of guessing that the area of the curve in that particular integral is going to be the same if we are dealing with the L periodic function. And that is what it means to say mathematically, is that integral a to a plus L. Now, you can see the, suppose here is a, here is a plus L. Now, if I have b here, this is b plus L, then a to a plus L f of x dx is equal to integral b to b plus L f of x dx for all a b in R, which essentially it is saying that in any fixed length interval of length L you take and you compute the area that is going to be same, it is irrespective of the position where you were choosing your integral. So, the proof, most of you might have seen this. So, let us just recall it quickly. Now, if I left hand side, I write a to a plus L f of x dx, which I will do that this is 0 to L f. So, now I have a to a plus L. Now, I will take this is 0 to L. Now, f is defined everywhere. So, 0 to L f of x dx. Now, plus I add L to a plus L. This now, I want to get back this integral, because this is a to a plus L. So, I need to subtract from 0 to a, this part I need to subtract. Therefore, this is going to give me the a to a plus L. Now, this integral is 0 to L. Now, if I make a change of variable f of x plus L 0 to a f of, then here x plus L means this is 0, this is a, and here I have minus 0 to a. So, this gets cancelled. I will get that this integral is equal to 0 to L f of x minus of f a, and that essentially is equal to 0 to L f of x dx. Similarly, I can show that b to b plus L f of x dx is again 0 to L f of x dx. Therefore, it really does not matter where you are choosing your interval. What it matters is that if you have a L periodic function, you have every freedom to choose your interval. Thank you.